Alright everybody, I still have not figured out the technical issue with my tablet and laptop. It is definitely perplexing me, so I'm a little bit limited in my abilities. I'm just going to be recording off of the tablet itself. So, to display the first question, and now to solve it, we're going to go through the entire question, by the way. So we have react to produce CO2 aqueous and what we're going to do is calculate, in order to do this at 338 Kelvin, we need to get thermodynamic data and calculate delta G at 338 Kelvin. So we have, and I'm just going to put in all the values. And the entropy so with these values, we are able to calculate the reaction enthalpy and the reaction entropy. And then calculate the delta G at any temperature, the equation that we have where, as we've shown previously, delta H and delta S are relatively independent of temperature. So delta G at 338 Kelvin is that value there. To calculate the cell potential, another equation we have for delta G, standard cell potential, is minus the number of electrons times Faraday's constant times the cell potential. In order to calculate the number of electrons transferred, we can go up here and we can assign oxidation states. 0, minus 2, plus 4, minus 2, plus 1, plus 1, plus 1, minus 2, and that ultimately makes the carbon minus 2. Looking at carbon as it moves, that's a 6-electron process for carbon to go from minus 2 to plus 4. Or we could look at oxygen, and it doesn't matter which oxygens you look at, it goes from 0 to minus 2. And since there are 3 oxygens that do this, this is also a 6-electron process. It needs to be balanced. If that was confusing, just go through and balance this equation via half reactions, and you will find that 6 electrons need to be transferred in order to get the balanced half reaction, or a complete reaction. So, number of electrons is equal to 6, and you do that and rearrange this to get E cell. And you find out that the standard cell potential is 1.170 volts. That was part A. Part B says that this system is not reacting under standard conditions. We are reacting under non-standard conditions. So to calculate the cell potential under non-standard conditions, we need to use the Nernst equation. Where, if we go back up to our equation, we find that Q, realizing the states of matter here, states of matter are important. We're making CO2 that is aqueous, not gaseous. We are using gaseous oxygen, but our methanol and our carbon dioxide are in aqueous form. And so using the standard reporting states of matter, this would be the concentration of CO2, because it's aqueous, over the concentration of methanol, times the partial pressure of oxygen raised to its stoichiometric coefficient. And so to look at all of the values that we have, of course, the number of electrons transferred is 6. The temperature is 338 Kelvin. And our Q is 1.5 divided by 3 times 0.209 raised to the 3 halves power. Plug all of that into a calculator and you get 1.162 volts. Again, not a lot different than the value we had above of 1.170, but it is different because we're not working under standard conditions. Part C says that the system is 55% efficient, and we are asked what methanol flow rate must be used to produce 150 watts of usable power. Well, a couple things come out of this. P is equal to VI. That is the relationship for power, current, and voltage. And we're interested in the current. The voltage isn't going to change as long as the conditions stay the same. What changes is the number of electrons being transferred. And this is power over volts. So in order to know what current we have 150 watts. And our voltage under these conditions is 1.162 volts. And this is going to give you 129 amps. Now, that 129 amps is at 100% efficiency. We're not at 100% efficiency, we are at 55% efficiency. So, do we need a number that is bigger than 129 or smaller than 129? And the answer is you ultimately need a number that is bigger than or 129. So to factor in the efficiency calculation, you're going to either multiply or divide by the 0.55 to give you a number that is bigger than 129. And the answer is simply to divide by 0.55, which is the efficiency. And when you do that, you end up with 235 amps, which is what you need. You need to produce 235 amps because only 55% of them are actually going to be usable power. And so 55% of this is 129 amps. This is how one would rationalize that above calculation. So in order to calculate this value, you simply move this over to that side. Now what do we do with it? Well, an amp is a coulomb per second, and this is simply just a series of units conversions. So we are going to take 235 coulombs per second, and let's start working with units. Let's get them to things that we know. Well, we can convert to moles of electrons using Faraday's constant. 96485 coulombs per mole of electrons. We know from the chemical reaction that we have 6 moles of electron for every 1 mole of methanol used. And we know the concentration of methanol is 3 moles per liter. So when we go through and start looking at the units here, moles of electrons cancel, coulombs are canceling, moles of methanol are canceling. That's a good start. And we're left with units of liters per second. Oops. Liters per second. And we were asked in the problem to convert liters per minute. So to do that final conversion, it is 60 seconds per minute. And what we have is 8.1 times 10 to the minus 4 liters per minute. Or 0.81 milliliters per minute. Actually, my error, it's minus 3. I'm trying to figure out where I've made an error in this calculation. This is minus 3, and so this is 8.1 milliliters per minute. That's better. 8.1 milliliters per minute is the flow rate of the methanol solution required to produce 150 watts of usable power. All right, so moving on, I actually did do the next question as well, but I want to, I made an error in class. I forgot one minor thing, so this is the question that we're going to be working on. And so for this question, the chemical equation that we have is that of 2 iron plus 3 halves oxygen reacts to produce rust. We are told that the cell potential is 1.282 volts. And in order to figure out if the value is going to be lower or higher, well, one would realize that we are working with a partial pressure of oxygen of 0.209 volts. And that being less than 1, it means that this driving force in this direction is less than it would be if it was 1 bar. So the potential should be less than 1.282 volts. But we're going to calculate that to confirm. Using the Nernst equation. And since we're at 298 Kelvin, I'm just going to use this equation. We have log Q. Once again, we need to figure out the number of electrons being transferred. And so assigning oxidation states, those are 0, minus 2, plus 3. Because we have 2 irons being transferred, if one were to look at the irons, you would have 6 electrons there. Similarly, we've got 3 oxygens being transferred, so it's a 6 electron process there as well. Again, if you need to balance it via half reactions to figure out the number of electrons, that's fine. Plugging all what we know into this process, we have 1.282 volts. And Q, and by the way, this is where I made the error in doing this in class. I needed to take into account the stoichiometric coefficient. Everything else is solids, so Q here is simply 1 over the partial pressure of oxygen raised to its stoichiometric coefficient. And so this is 1 over 0.209 volts atmos bar raised to the power of 3 halves. When you do all the math here, you get 1.272 volts. All right, so that answers that question correctly. This is the next question we're going to be looking at. And this question simply requires us to determine the cell potential for the following reactions. And the reactions that we have going on are zinc, solid, that should be it. There we go. All right. Better. So we need to break this up into oxidation and reduction half reactions. Remember, oxidation is on the left, reduction is on the right. And as we write these out, it actually does flow that way. So I have zinc solid, which is my electrode, going to zinc 2+. That electrode clearly has to be active because zinc is being removed from the electrode. To balance this, I'm going to need 2 electrons, and I need the reduction potential as well of negative 0.762 volts. That's just simply looked up on the data sheet. The second reaction is that of iron 3+ reacting to produce iron solid, and this is a 3-electron process. The reduction potential here is negative 0.037 volts. What do we do with it? Well, we balance the number of electrons, which needs to be 6, not 6 of those. We're going to have multiply the top one by 3, 3, and 6, bottom one by 2, and we have something where the electrons cancel out, which is great. The balanced half reaction is that of 3 zinc solid plus 2 Fe3+ reacts to produce 3 zinc 2+ plus 2 Fe solid. That's better. Now the brightness isn't going to change. The cell potential is calculated using cathode minus anode, and realize that the first one is an oxidation, second one is reduction. Cathode minus anode gives us 0.725 volts, which is what we were after. To do the next reaction, I'm not going to do it in full, but it is the reaction of magnesium again protecting iron. The only thing that changes is the magnesium reaction, and for the magnesium reaction, the reduction potential is negative 2.356 volts. And if you were to go through the entire process up above, similarly, you're going to find out the cell potential is 2.319 volts. And it is done in exactly the same manner as what was done above. This is the next question we're going to be looking at. And it's the electrochemical cell for concentration cell. And we need to figure out the formation constant Kf of the copper 1 chloride complex ion. So there's two things that we need to understand here. We need to understand what's happening from a chemistry perspective, and we need to understand what's happening from a measurement or the current perspective. Current as in electrochemical cell perspective. So from the chemistry, the chemistry says that we have a cell that is being controlled by the complex ion formation of copper plus chloride reacts to produce this complex ion right there. We have an ice table we are going to set up on this, and we don't have the ability to fill in the ice table yet, but we can know our initial conditions. We have as initial conditions, we have as initial conditions 50 mils of 0.2 molar copper nitrate and 200 mils of 0.2 molar hydrochloric acid. So here, I'll be able to erase this in just a few seconds, we can calculate the concentration of copper as simply the dilution, 0.20 moles per liter, times 50 over 250 milliliters. That is simply an application of C1V1 equals C2V2, and that will give us a copper ion concentration of 0.040 moles per liter. You do the exact same thing with the chloride and you get 0.16 moles per liter. And of course, we don't have any of the complex ion as of yet. All right. What we need to do is we need to start finding these numbers. If we can find these numbers, then we can calculate the formation constant. And we get those numbers from the electrochemical cell. And so from a measurement perspective, all we have are two half cells, each with copper in them. And so I have copper solid, reacting to produce copper ions plus an electron. And in the other cell, I've got copper ions plus an electron reacting to produce copper solid. We suspect that the test cell is of lower concentration, given that it is forming a complex ion. And as a matter of fact, just by its mere dilution here, it originally starts off with a lower concentration. So we're going to say that this one wants to produce more copper ions because it is of lower concentration. If you mess this up, you're just going to get a negative sign. It's not going to be a big deal. Test cell because of lower concentration. And the other one will be our reference cell. So when we put all of these things together, I'm just going to switch back to black, we end up with copper plus copper ions in the reference electrode, right? Copper ions, reference electrode, is reacting to produce copper ions in the test electrode plus copper solid. The reference electrode has higher concentration of copper, so it wants to go down, and the test cell has a lower concentration of copper ions, so it wants to go up. From this Q, from our concentration cell, would be simply the copper ion concentration in the test cell over the copper ion concentration in the reference cell. All right, so plug these things into the Nernst equation. what do we know? If everything was standard, if all the concentrations were 1 mole per liter, there would be no voltage. Q would be equal to 1, and so E, the standard cell potential, is 0. If everything's 1 unit activity, there is no voltage. There's no driving force to change the concentration. So with that removed, we also know the number of electrons transferred in this process is 1. So we can substitute in what we have from our question. And this was at 295 Kelvin. 1 mole of electrons, and that's coulombs per mole of electrons. Log Q is our unknown copper ion concentration in the test cell. Over its known concentration in the reference cell, which is 0.5 moles per liter. So as everything gets rearranged, we can rearrange this to get the log of the copper ion concentration in the test cell over 0.5 moles per liter in the reference cell is equal to, this is just algebra, negative 2.699. And when you remove the logarithm and multiply by 0.5, you find out that the copper ion concentration in the test cell is 1.00 times 10 to the minus 3 moles per liter. See that many significant digits. It is this number here, wrong color, that goes into the ice table. Okay, into the ice table. So I'm just going to go way back up to the ice table that we created over here. And we now have this value being 1, we know at equilibrium that this is 1.00 times 10 to the minus 3 moles per liter. And so we can sit there and go, this is minus 0.039, minus 0.117, 0.039, 0.039, and 0.043. That is the completed ice table. Now we have everything at the equilibrium level, and unfortunately I'm going to have to scroll to the bottom. We have an equilibrium constant, K, which would be equal to that, as presented there. And when you plug all the values in from up above, you get 4.9 times 10 to the 5 liters per mole cubed. And the units come from the equilibrium constant. If you look at the equilibrium constant over here, concentration divided by concentration to the 4th gives you 1 over concentration cubed. So that is how that is done. This is the next question we're going to be looking at. And with this question, we are doing some electrorefining of aluminum. And we're now working at industrial quantities, but our knowledge deals with chemistry-related, laboratory-related stuff. So first thing I want to do is I want to take that 1 ton of aluminum and convert it into something I know, which is moles. So that's 1,000 kilograms per ton. 1,000 grams per kilogram. And 1 mole of aluminum is 26.96 grams of aluminum. When you plug all that into a calculator, you get 3.709 times 10 to the 4 moles of aluminum. Aluminum only has one oxidation state, and that is the aluminum 3+ ion. So the reaction is a 3-electron process. What we are asked, I should remind you of that, is how long does it take to produce 1 ton of aluminum? Well, that infers a unit of time. And we have, in terms of our example, our question, the current at 100,000 amps, which is coulombs per second. So taking the moles of aluminum, I need to convert to coulombs and then figure out how long it's going to take. So taking this value down here, three moles of aluminum per 1 mole, 3 moles of electrons per 1 mole of aluminum. Coulombs per mole of electron, and you find that this is equal to 1.074 times 10 to the 10 coulombs. Again, 1 ton of aluminum, quantities that we're not used to with, so the values in terms of the charge here is huge. And, well, do the calculation enough times to convince yourself that you haven't made a mathematical error. In order to get the time, we have the relationship Q is equal to current times time, or the other relationship, current equals charge over time. They're exactly the same. Both of those, depending on what you learned in physics, I want time, which is charge over current. And if we plug the values in, we got 1.074 times 10 to the 10 coulombs over 1.0 times 10 to the 5 amps. And we're calling amp is a coulomb per second. So when you do the math, you end up with 1.074 times 10 to the 5 seconds, which is really valid only to 2 significant digits. And when we continue this on, this is actually 29.8 hours. $29.8. And part B asks us to figure out how much does it cost for this process. So we're back to power, oops, wrong color. P equals VI. Get us the power, 5 volts times 1 times 10 to the 5 amps. This is 5.0 times 10 to the 5 amps, or excuse me, watts. Or 500 kilowatts. Now to convert to cost, there isn't a formula, or potentially there is a formula. It's literally units conversions. We want how much does it cost. So picking something that might be reasonable to start with, let's go with 12.5 cents per kilowatt hour. We know we have to run this for 29.8 hours, and we have 500 kilowatts. So that means kilowatts is canceling, hours is canceling, and we end up with 1.89863 times 10 to the 5 cents. Okay, or to convert that into dollars, this is $1863. But if we look at the problem, this is 100% efficiency. We aren't at 100% efficiency, we are at 92% efficiency, so it's going to cost more in order for that to occur. So if I divide by 0.92, I get a value of $2,024. Valid to two significant figures. And this is the last example we're going to be looking at. And in this example, we are going to be doing some electroplating. So the first thing we need to do is determine the mass of nickel required to do the plating. And simply following the units through, we have 190 centimeters squared times 50 micrometers. That's going to give us a volume, the area times height. But we need to convert that to centimeters, and I don't know the direct conversion from micrometer to centimeters, so I'm just going to go 1 meter is 10 to the 6th micrometers, and there is 100 centimeters in a micrometer. If you know the direct conversion, all the more power to you. I'm not concerned. I can go through two steps where I know the value. This is 0.95 centimeters cubed. And if we multiply by the density of nickel, 8.91 grams of nickel per centimeter cubed. Of course, the volume cancels. And we find out that we have 8.46 grams of nickel that has been plated onto this dinnerware set. Part B asks to figure out how to do this. You need to know the common oxidation state of nickel, and there's actually only one. It happens to be nickel 2+. And yeah, that comes from just looking at the electronic configuration in Chem 100. And once again, we're needing to figure out time, and that requires Q equals IT. So we need to go to charge. And so starting with our 8.46 grams of nickel, convert back to moles. Over 58.569 grams of nickel. And we know there's 2 moles of electrons for every 1 mole of nickel. And we know it's 96485 coulombs per mole of electrons. Grams, moles, moles of electrons. And all is said and done, you get 2.78 times 10 to the 4 coulombs. Now we just did this in the last problem. Q is equal to I T. T is equal to Q over I. T is equal to 2.78 times 10 to the 4 coulombs per 300 coulombs per second. That's the amps. And this is 92.7 seconds. And those are all of the examples that I needed to present to you the process for which they are done. Thank you for paying attention to this.